Okay, hi everyone. This is week number 8, lecture number 8 in CHEN 430 process design. In this lecture, we'll continue talking about heat and power integration and heat targeting, building on the ideas we covered last week from, using the algebraic approach, using the graphical approach to find your pinch point, to find your minimum energy requirements for your process, and how can we translate this information into a design for our network. Okay. So just a couple announcements before we kick off. Week number 8, October 12, we will be talking about heat and power integration, and then we're going to have an Aspen review session this week, so there won't be a new Aspen tutorial covered this week. Your Aspen tutorial number 6 is due this week, and of course you have 2 weeks from today to submit it without any penalty. And your project deliverable number 1 is due, which is your process overview and background, okay? After you submit your first deliverable, expect some feedback from me about your deliverable in terms of how you present yourself, how you write the technical report, and other aspects in that regard. And project deliverable 1 is not weighted heavily, so it's going to be graded harshly, but use it as a learning experience to to optimize your approach and optimize how you approach a project, how you submit your deliverables, etc. Okay, let's move on. So the objectives, if you recall, last time we said, if I give you some data on hot and cold streams of a process, you should be able to calculate the pinch temperature, whether using the algebraic method or the graphical method. We had the homework as well, which we practiced this a bunch of times. And you should also be able to compute the maximum energy recovery targets using both graphical and algebraic methods. So what are we going to do this week? So now I give you a bunch of hot and cold streams. You got the pinch temperature, you got the maximum energy recovery requirements. So let's translate this information into a heat exchange network, right? So how do we use this information to make a decision on which hot stream to connect to which cold stream? And where do we make these connections? Do we make them above the pinch, below the pinch? All of this stuff. This is what we're going to cover this week. So if you recall the motivating example from last week, where I had a process. In this process, I have 2 reactors right here. And then I have a distillation column. I have 1 cold stream entering. It's being heated to 120. And a second cold stream at the very end, it's being heated to 100. I also have a hot stream here coming out of this reactor being cooled to 180. And I have a second hot stream from the bottom of the distillation column being cooled to 40. And you're told that you have utilities, which is steam at 150 and cooling water at 25. And you're given the stream information, which is, source temperatures of all the streams, the target temperatures of all the streams, the enthalpy change, and your mass heat capacity. And if you recall, your original objective was to design a network of steam heaters, water coolers, and exchangers, which we did not achieve last time in a systematic way. What we did last time is we just found the pinch point, and we found the minimum energy requirements. So we said, if you try to connect them haphazardly, logically, you would connect the hot streams to the cold stream, try to, integrate this energy, and then make the balance using the utilities. So in this case, I'm using this hot stream being cooled to 40, and I just use the energy to completely heat up this cold stream, and whatever energy needs to be removed, I just add a cooler. On this side, I use this hot stream, which needs to be cooled from 180 to 80 to completely heat up this cold stream, which has to be heated up from 60 to 100. And whatever energy remaining or whatever energy left has to be added, I just add a small heater here to supplement it, okay? And this was sort of a design. We never really talked about how did we get this design? Why didn't we connect the other 2 legs? Why is this option better than the other option? We didn't really cover this last time. We just said that what we did last time is you basically found how much this value is and how much this value is, and we said this is your minimum energy requirements. And then we also found something called a pinch point. Okay, and if you recall last week, we said the way to approach it graphically is I'm going to plot for each stream, I'm gonna plot a line, and this line starts from your target temperature, starts from your source temperature, sorry, to your target temperature, and it has a slope equivalent to your CP. Alternatively, you can just start here and then move a distance equivalent to delta H, and you'll have your line. You draw both lines for both streams. If you have a bunch of streams, you'll draw all the lines. And then each interval, I'm gonna recognize either, or I'm gonna write down either the delta H, or alternatively, if not the delta H, then I'm gonna write down the summation of CP, right? And both approaches work. So if you want to use delta H and use, you know, the your x-axis to connect them, you can do that, or you can use the summation of CP. So summation of CP in this segment will be 1. Summation of CP in this segment will be 3. Summation of CP in this segment will be 2. And then I connect them by basically starting at this point. So from this point, from this temperature to this temperature, I have a delta H equals 80 and CP equals 20. So CP equals 2, sorry. So I draw a line with a slope of 2. And then from this interval, in this interval, basically, I have a delta H of 150. So you can either move 150, or I can draw a line with a slope of 3. Both will achieve the same thing. And then this interval, you know, I can either move 50 or draw a line with a slope of 1, whatever it is, and you get your composite line. And this is called the hot composite. And this is what we get. You get a composite curve called the hot composite stream. And this curve is only obtained using your hot streams, right? This is called the hot composite curve, of course. Similarly, or you know, on the opposite end, I do the same with the cold streams, right? So for the cold streams, I identify the source temperature, the target temperature, delta H, and you know, for example, so I can either draw a line with this delta H equal to the delta H of the stream, or I can just draw a line with a slope equals to 1.8. I do it for both streams, and then in each interval, I look at the summation of CP. And similarly, that's how I really draw the composite curve. If you don't want to use summation of CP, again, you can use delta H, it's up to you. And you just connect these lines to get your cold composite curve. Okay, and once you have your hot composite curve and your cold composite curve, so once I have my hot composite and my cold composite, I'm gonna overlay both of them onto one figure. So this is my hot composite, this is my cold composite. And then I'm gonna basically shift the cold composite until the minimum distance between these two lines is equal to delta T minimum. Okay, so you just overlay them, and then you move them closer to each other by shifting the cold composite until the minimum distance between the lines is equivalent to delta T minimum. And once you get to this point, this temperature here, this is your pinch point, basically. Sorry, pinch point. And then we have this value here, which is the difference between the ends of the lines at the top. This is your, you know, QH minimum. And I have the distance here, the difference between the two lines at the bottom or at the left end. And this is QC minimum. Okay, and these are called your minimum energy requirements. This is called your pinch point. And we said the whole idea of having a pinch point is that I can divide this problem into two smaller problems without and really minimizing the possibility of violating thermodynamics of heat transfer. So, okay, so this is the pinch. This is your QC minimum. This is your QH minimum. And these are referred to as your maximum energy recovery, right? Or, you know, your energy recovery targets. So how do I translate this information into a heat exchange network? How do I translate this? I just have 3 numbers. I have a couple of graphs, or maybe you did using the cascade diagram. You have a nice tree there, and you got these numbers. How do I translate it into a design? So how do I jump from here to this design? In order to do this, we need to build this type of figure, and this is called a heat exchange network, right? So I need to translate my MER plus pinch into this figure, and this is called the heat exchange network, okay? And this is very important. Right? This is very important. We're gonna have a look at it in the next slide. Okay, so this is the heat exchange network. So what's the first thing you notice about this? First thing, yeah, you notice is that I just have all my streams, my hot streams and my cold streams just drawn out horizontally, right? So I have my stream H1 and I just draw it out horizontally. I write my starting temperature here, which is my source, and I write my target temperature here for all of them. So H2, again, 130 to 40. C1, it's flipped, right? So for this will be your source. This will be your target. And C2, this will be your source, and this will be your target. So the first step in building this diagram is that I'm going to just draw all of my streams in this fashion, right? And again, your hot temperature is always on the left, right? Your higher temperature is always on the left. Whether it's a cold stream or a hot stream, higher temperature always on the left. So after doing this, I'm going to divide the problem into a hot problem and a cold problem, right? And so, and this is hot, basically this will be your hot problem and a cold problem, and we need to define two terms. So this side here, this is your left-hand side, and this is called above the pinch. And this is your right-hand side, and this is called below the pinch, right? And if you think about it, it makes sense because the temperature here, you know, we always have a higher temperatures on this side than this side. So I divide into two problems, two parts, left-hand side above the pinch, right-hand side below the pinch. And at this pinch, all the hot streams are hotter than all the cold streams by delta T minimum. So this distance here is equal to delta T minimum. And we're gonna have a look. I mean, once you practice it becomes, you know, more obvious, but this is really a systematic approach, right? So you just follow the steps to achieve it. So let's have a look at an example. Let's have a look at an example here. So let's say I give you 4 streams, right? I give you 4 streams with this information where I told you I have H1, H2, C1, C2, H1, its source temperature is 170, H2's source temperature is 150, C1, the source temperature is 20, and C2, the source temperature is 80. The target temperature for H1 is 60, target temperature for H2 is 30, target temperature for C1 is 135, and target temperature for C2 is 140, and you're given some CP values, 1.524. Okay, so you're given this in a table, or you extracted it from a process diagram, whatever it is. So the first step is to translate it into this format, okay? And as you can see, I just draw horizontal lines, starting with the hot stream. So basically, I draw a square or a circle, write the stream name H1, I draw a horizontal line all the way to the end, and then I write at the start of the horizontal line my initial temperature. At the end of it, I write my final temperature, and it's always good to write your CP values here as well, just to take note of them. Similarly for H2, I just, you know, label it, circle, whatever, diamond, whatever you're happy with. Starting temperature, final temperature, I just draw a horizontal line, and 1.5, I write my CP. And as you see, I'm not using any scale. I'm just drawing lines to represent these streams, right? So I'm not really sort of plotting or anything like that. And again, for C1, 20 to 135, for C2, 80 to 140. So after you do this graphical step, let's try to build our heat exchange network. So step 1 will always be to find your pinch and divide your problem, okay? Or basically just draw a line in the middle of So basically, step one, so at this stage, of course, you already know your pinch point and you already know your energy targets, right? Because this step comes after whether you draw your hot and cold composite lines or you did your cascade diagram, right? So these will be step one. These will be basically done before. And from this step, you have your energy targets and your pinch point. And once you have this information, now we're going to build our network. And the first step in building the network is just graphically drawing your lines. And then, you know, step one, MER targeting. So step one really is doing these two guys, getting this information. And then we're going to draw this. And then once we have this, we need to divide the problem at the pinch. So as you can see here, I just split my problem at the pinch. I found my pinch point. So the pinch point is 90. I just draw a line in the middle with 90. And I divide my problem into a hot problem and a cold problem, or above the pinch and below the pinch. Let's go back and have a look. So in this case, my pinch was at 90 for the hot streams and 80 for the cold streams, right? So all you need to do really is just graphically the standard method or the procedure to be followed is I'm just going to draw two lines, right? On this line here, on the hot streams, I'm just going to write the hot pinch temperature. And on the cold streams, I'm going to write the cold pinch temperature. And you have to be careful because, you know, sometimes, you know, 80 to 140. So, you know, this stream actually starts here. Okay, so just be careful. Sometimes your stream, you know, ends here. So if it's a hot stream, it might end here, or, you know, it doesn't matter. Just draw the two lines for your pinch point and write your temperatures for the hot pinch and the temperatures for the cold pinch. Okay. Again, just do it slowly. Once you get to this point, just be careful about your temperatures. Don't just, when you're solving a design problem, always, even though a lot of the time we're just following a procedure or following an approach, you need to be cognizant of all the numbers you're dealing with. You need to keep an eye out. If something doesn't make sense, you need to catch it, all of this stuff, okay? So I divided the problem into at the pinch, basically. As you can see for the hot streams, my pinch temperature is 90. And for the cold streams, my pinch temperature is 80. And of course, the difference between them is the delta T minimum. Okay. So once I've done this, my problem is divided into two problems, right? The first problem is here, this is the hot side or the hot end or above the pinch, whatever you want to call it. So this is problem number one, and this is problem number two below the pinch. I divided my system into two smaller problems, and now we're going to look at them one by one. First of all, let's look at the hot pinch or the left-hand side or above the pinch, whatever you want to call it. So in this side, I'm going to pair up exchangers according to CP constraints. And above the pinch, you need to pair up streams such that CP hot is less than CP cold, okay? So above the pinch, this is what I have above the pinch. I need to look at my CP values and determine which combinations are thermodynamically possible. And what governs which combinations are thermodynamically possible is this rule right here. And this is extremely important, okay? I can only connect streams if CP hot is less than or equal to CP cold. This is the only way you can connect these streams. Otherwise, it's not possible, okay? Again, let's go back here for a second. So I'm given some information about some streams. I drew the horizontal lines, representing the streams graphically or on your graph or on your worksheet or on Excel, whichever way you want. Then I'm gonna draw a line in the middle. This will be my pinch point. And for the hot streams, the pinch point is always greater than the pinch point for the cold streams by delta T minimum. I divide my problem into two sides. Left-hand side called above the pinch, right-hand side called below the pinch. And then I'm gonna look at each side separately as its own separate problem. And above the pinch, I need to connect some streams. So I have a lot of energy going on above the pinch, right? So if you think about it, you know, this 170 to 90 and CP equals 3. So delta H available in the stream is equal to what? 170 minus 90, that's 80 multiplied by 3, 240. So I have 240, whatever units it is. For this guy, I have delta H, and this is only above the pinch. 150 minus 90, 60 by 1.5. This is 90. For this guy here, I have 135 minus 80. So it's 55 by 2, it's 110. And for this guy right here, I have 140 to 80, that's 60 by 4, 240, right? So I have a lot of energy. So the hot streams need to lose 240 and 90, and the cool streams need to gain 110 and 240 above the pinch. Whereas below the pinch, the delta H for this stream below the pinch, 90 minus 60, 30 by 3, it's 90. For this guy, 90 minus 30, 60 by 1.5, that's 90 as well. And for this guy, delta H is 80 minus 20, 60 by 2 is 120, right? So on below the pinch, I have two hot streams, each needs to lose 90. Then I have a cool stream, which has to gain 120, right? So there are rules to determine how do we connect these streams. So, I mean, intuitively you might say, oh, okay, I'm gonna connect this guy to this guy, then I'm gonna connect this guy to this guy, and then whatever is left, I'm gonna add a heater here. Maybe, I mean, intuitively it might make sense, however, this violates the rules. And the rules you need to follow are this, that above the pinch, you cannot connect streams unless the CP of the hot temperature stream is lower than the CP of the cool stream, right? So basically, if I go back here, and we said above the pinch, the rule which applies CP hot has to be less than CP cool. This is very important. So if I start with the hot stream, the CP here is 3. So the CP for the hot stream in this case is 3. You cannot connect hot to hot, just forget it, doesn't work. I look at the first CP cold, so CP hot less than or equal to CP cold. So this doesn't work. And then sorry, so we'll just continue here. So above the pinch, I need to meet the CP hot has to be less than CP cold. So in this case, I have H1. CP hot is 3. I look at the first cool stream, it's 2. So 3 is 3 less than 2? No. So this connection is not valid. It's not thermodynamically possible. I move on to the next cool stream. 3 is 3 less than 4? Yes. So this connection is possible. So thermodynamically, this connection makes sense. Whereas this connection does not make sense. Let me write another color. You know, thermodynamically, this connection right here, connecting 1 to 3, does not thermodynamically sense because CP hot is not less than CP cold. Okay, this is very important. You need to remember this. Whereas this one makes sense because CP hot is less than or equal to CP cold. Okay, so after you're done with the first stream, I move on to a second hot stream. So I get the pen here. So my first hot stream, and I connected it to this cool stream. Sorry, I connected it to this cool stream because, you know, these two match. Let's have a look at how much energy can I transfer. So this one has 240 to give. This one needs 240. So, you know, this looks like a reasonable transfer. So I'm going to transfer all of the 240 here, right? So this heat exchanger transfers all this 240 energy, and I basically satisfied the energy requirement for this guy and satisfied the energy requirement for this stream right here. Let's move on to the second hot stream, 1.5. I only have one option really because stream number 4 is done. It doesn't have any more energy to take. So I need to see, is this thermodynamically possible? Is the CP of the hot stream less than the CP of the cool stream? It is. So it means that thermodynamically I can connect them. So you just connect them. You draw your heat exchanger right here. and you find out how much energy can I provide. So in this case, the hot stream has 90 and the cool stream needs 110. So I'm going to, transfer 90 in this case. And if you recall from last time, we had two rules, right? We'll get to them in a second, Where is heating allowed? Where is cooling allowed? You can't heat somewhere, you can't cool somewhere, and this will really control the flow of energy. So let's have a look at the next slide. So again, we said immediately above the pinch, we need to pair up streams such that CP hot is less than or equal to CP cold. And if we try to pair up, for example, H1 with C1, where CP, the CP in this case is 3, CP is 2, so it does not meet this rule. If you try to draw your heat exchanger temperature profiles, you'll find out that it violates the delta T minimum constraints. So there isn't enough driving force for this transfer to happen, right? So even if I connect them, they're not going to transfer heat because there is no driving force for this heat to move. Okay, thermodynamically it won't work. Okay, so then I look at this one for CP hot. I connect it to stream C2, which has a CP of 4, which meets this criteria of CP hot less than the CP cold. If you look at the profiles of a temperature, you'll find out that they always meets the delta T minimum constraint. So between these two streams, there's always enough driving force for this heat exchange to happen. Okay, so you use this logic to complete the hot end design by just sticking off streams. So as we said, we're going to connect H1 to C2. Again, you need to remember that about here that you need to meet this rule. CP hot has to be less than or equal to CP cooled. So you always start with the first stream and use a logical approach. Do it step by step. It doesn't matter. Start off with the first stream. CP is 3. I look at my first cool stream. Does it match? No. Does it match with this guy? Okay. And then I connect them, and then I look at how much enthalpy is available here. Calculate it. Again, delta T multiplied by CP. I look at how much enthalpy does this stream need. Look at it, and then I transfer all the heat which has to be transferred. So in this case, I transferred 240 units of heat. Okay, so what we did, this stream is satisfied, this stream is satisfied, so we don't need to worry about them anymore. And then you do the same thing for us. You move on to a second hot stream, 1.5. I can't really transfer any heat to the stream because there's no heat available, nothing left. I check with this guy, does it meet this rule, CP hot less than CP cold? Yes. Sorry, yes. So this connection is possible, which means that this connection is possible. So now I just connect them using a heat exchanger, and I calculate how much heat is available in the hot stream to give to the cold stream, and I just basically transfer this heat. And then you need to be aware that 150 minus 9060 multiplied by 1.9. So this stream had 90 units of heat to give, whereas this stream 135 minus 80, 55 multiplied by 2 is 110, right? So even though I transferred 90, I still have 20 units of heat available, which are not satisfied for the stream. So what do I do now, right? I add the heating utilities as needed. And this will help you verify whether your cascade or graphical method is correct, because the remaining amount of heat in the stream should equal your QH minimum, which you calculated from your cascade diagram or from your graphical diagram. So in this case, in order to satisfy it, I just add a heating utility with 20. And this number must match the number you get from your cascade diagram. So this must match this number here. If it doesn't match, this means your connection is wrong, or you just did a calculation error somewhere. Okay, if the numbers don't match, you did a calculation error somewhere, go back, double check all your calculations, your steps. Maybe when arranging your intervals, you missed the temperature and you're missing an interval, something like that. Just go verify your calculations. One thing you need to remember in this case that above the pinch, there is no cooling, okay? This is extremely important to remember, okay? So this is, above the pinch, you need to remember two things. This is the first one. Second one, there is no cooling above the pinch, okay? You should never have a cooler here. Doesn't make sense thermodynamically. It doesn't make sense in terms of process design. It's just a waste. So there is no cooling above the pinch at all, okay? So if you connect them somehow and you still have some energy left in your hot streams, you did something wrong with your calculations. Verify your calculations. Above the pinch, you should always have energy left in your cool streams, and you just install a heater to meet the balance. You should never have cooling above the pinch. Again, above the pinch, remember two things. When connecting streams, you follow this rule, and then no cooling. Never cool above the pinch. All right, moving on. Below the pinch, we have a similar logic. However, below the pinch, I'm following the reverse rule. CP hot has to be greater than CP cold, okay? And this is below the pinch, and you follow the same logic. So again, if I have a bunch of streams here, I have two, and when you're looking at, below the pinch, you can, I mean, usually you start to C1 and you match them, but you can start with H1 and you move downwards, it doesn't matter. You're gonna get the same thing. I mean, you might have two, three different designs, but your heat targets will always be the same. So I start with C1, I compare it to the first one here. Is CP hot greater than CP cold? No. So if I make this connection and I look at the flow profiles, I'll find out that it violates delta T minimum constraints. So there is not enough driving force for this connection to work thermodynamically. So this connection is not valid because it violates this rule right here. I look at the second hot stream, 2 with 3. Is CP hot greater than CP cold? Yes, because if you look at your temperature profiles, you'll find out that the driving force or delta T minimum is always maintained. So there's always enough driving force to push this energy between these two streams. There's always enough driving force for this transfer to happen. Okay, so once you find the two successful pairs, or the pair, successful pair between the cold and the hot streams, you connect your heat exchange network, you calculate your delta H, and you just do your math. Let's have a look here. So this is above, this is below the pinch. For the problem we're just covering, I have C1, H2, and H1. So let's try connecting them, right? So C1, CP of 2. And again, let's remember the rule here. Again, there are two rules below the pinch. Number one, CP hot has to be greater than CP cold. And number two, no heating, right? You should never heat below the pinch. This is very important. If you find out that you need to heat below the pinch, your numbers are wrong. Just go revise them, fix them, take a second look. The most common errors is usually when building your cascade table, you missed an interval temperature, or you forgot to subtract the delta T minimum, or when drawing this, you confuse the hot pinch with the cold pinch, use the wrong delta T minimum. These are all common errors which result in these types of mistakes. But anyways, let's go back here. So below the pinch, I need to connect them such that CP hot is greater than CP cold. So I start with C1, I compare it to the first H1. Is CP hot greater than CP cold? No, so this doesn't work. I'm gonna compare it to this guy. CP hot greater than or equal to CP cold? Yes, so this connection is valid. So what I'm gonna do, I'll just draw a heat exchanger from here. And of course, you draw a straight line. And now I need to calculate how much energy is transferred. So this stream, 90 minus 60 by 3. So this is what, 90. So this stream right here has 90 units of energy to give. This stream right here, 80 to 120. What's that? 80 to 20. Is that 60? Multiplied by 2, that's 120. So this stream has a energy requirement of 120. So how much energy can I give if there is no heating above the pinch? So you connect them, you determine that I'm actually transferring 90. So this stream is satisfied right here. Take it off. However, this stream right here, I still have some energy remaining. I still have 30 units of energy, which I need to deal with. Okay. Let's have a look. Does this work? One sec. Let's go back here and see, are we violating the rules? Does this make sense? Okay. So immediately below the pinch, we said that CP hot has to be greater than CP cooled, right? So we already established that this transfer doesn't work, whereas this transfer works. Okay, so in this case, we matched the first two streams. We transferred 90, we have 30 units of energy to give. And let me just pause for a second and have a look. Okay, let's go back to this example. So we're talking about connecting our cold streams to our hot streams below the bench, and we said two rules apply. First one, CP hot has to be greater than or equal to CP cooled. And the second one, is that, you know, I can't have any heating below the pinch, okay? So these are two very important rules. So we started off by the first stream right here. Let me get the pen. Start off by looking at the first stream, C1, compared it to the hot stream, this 1.5, this connection doesn't work. Started looking at the second stream, C1 with CP. 2 and 3, this connection works because CP hot is greater than CP cooled. And I connected both streams, and now I determined that I can transfer 90 from the hot stream to the cool stream. Just this satisfies all the heating requirement for this stream. Okay, so now I've basically provided 90 units of energy for this stream, and I have 30 units of energy left. So how do I do it? You know, if you think about it, so this stream is satisfied. This stream, it needs 90 to 30, that's 60 multiplied by 1.5. So this stream requires 90 units of energy, and this stream requires 30 units of energy. However, there is no heating below the pinch. I can only cool below the pinch. So I can cool the stream. This will be thermodynamically valid, but I cannot heat the stream, right? It's not thermodynamically possible below the pinch. However, I still need to deal with this 30. And this is a common type of problem which you might see. And the way to approach this, and the reason why, you know, the slides show that this connection is valid, is because we're gonna introduce a concept called stream splitting, okay? And then again, this is very important. Please note this for your homework, for your exam as well, the idea of stream splitting, okay? And this is very common when dealing with these types of problems because you don't want to violate the rules. You don't want to violate the rule of having no heating below the pinch. However, I still have 30 units here, which I need to heat this cool stream. And I can't do it. So in order to do this, we're gonna introduce something called stream splitting. Let me just write it here. Stream splitting. And we'll start off by talking about CP. If you recall, we said CP is actually equal to M. CP, it's your mass heat capacity, where M is your flow rate, and CP is your heat capacity, right? Heat capacity is an inherent property of the fluid you have flowing in the stream, right? So the heat capacity cannot change, right? So if I have water or steam with a certain heat capacity, this is the heat capacity of the stream, it doesn't change. However, I can change M by splitting the stream. So if I have one stream, so let's say I have one stream right here with a CP equal to 2, which let's follow this example. So this actually equals M CP equals 2. If I split it into 2 streams, so if I split it into 2 streams like this, where I have, in this case, M1 CP, and in this case, M2 CP, right? If I look, these two are the same, right? So these two is just one stream, I just split it. So I just split this stream. So I can split it in a way such that M1 plus M2 or M1 CP plus M2 CP is equal to MCP. So if I write my mass balance here, M1 CP plus M2 CP is equal to MCP equals to 2, right? So if I basically cancel them all, cancel all these CPs, can divide by CP, of course, it doesn't matter. I'm gonna find out that if M1 plus M2 is equal to 2, then the split is valid, right? So if I divide this into basically 2 streams, one with 1.5 and one equal to 0.5, such that 1.5 plus 5 is equal to 2, then the split is valid. Because all I'm doing is I'm just splitting this value using the mass balance, right here. So this is called stream splitting. So if I have a stream with a CP of 2, and this is not working out for me, what I could do, or what you should do really, is you need to split the stream. So C1 is going to split. In some textbooks, the split is shown this way. And this is not a common case, it's a unique case, but it's going to show up in your homework. You can, some textbooks show the stream split this way. And what I'm doing is I'm splitting it into 2 streams. So in this case, I will split it into one stream, which has a CP of 1.5. And I'm splitting it into a second stream, which has a CP equals 0.5, right? And if you think about it, you know, M1 CP plus M2 CP is equal to MCP equals 2. So if I split them in a way such that basically this is 1.5 and this is 0.5, so I split the fraction. So I split where, you know, I take a quarter of the stream right here, and I keep 3/4 of the stream flowing. So the CP for the 3/4 is, you know, 3/4 multiplied by 2, 1.5. CP for the quarter, 1/4 multiplied by 2 is 0.5. I just split the stream this way. So now I have 2 streams which I can use in this heat exchange network without violating the rule of having no heating below the pinch. So this is what happened in this case. So if I divide it this way, so I'll have this stream with a CP of 1.5. Let me rewrite it. Okay. Okay. So I have this stream right here with a CP equals 1.5, and this stream can be connected to this stream without violating this rule. So CP hot greater than CP cooled. And then I have this stream where the CP equals 0.5, and this stream can be connected to this stream without violating this rule, right? Because CP hot is greater than CP cooled. And then this stream, you know, let's have a look, 80 minus 20 multiplied by 1.5. So the delta H for this guy is 90, and it's satisfied here. And if I look here, 60 multiplied by 0.5. So the delta H for this stream is 30, and it can be used to satisfy this transfer. So this is possible, and this is a trick which you can use either above the pinch or below the pinch. So you use it below the pinch to decrease the heating capacity of the cold streams, especially if you don't have enough cold streams, or you know, you find out that you have a lot of excess energy in the cold streams which you need to get rid of because you can't really heat. Similarly, above the pinch, you can use it to reduce the heat capacity of the hot streams because you can't really use cooling above the pinch, and these hot streams have energy which you need to deal with. So you do this stream splitting. And again, the idea is that the CP, capital CP here is equal to M. CP is equal to the flow rate multiplied by the heat capacity. The heat capacity is an inherent property of of the fluid, so this CP value does not change. So if I have a stream here with a CP equals to 2, if I divide it into, you know, 2 streams with M1 and M2, I can basically split this 2 over 2 streams, right? And as long as 1.5 plus 0.5 is equal to 2, your calculations are valid, your math is valid. This mass balance holds. Think about it, it makes sense. So basically, you know, I'm just, you know, making a fraction split, you know, splitting this 2 streams by splitting the mass balance. Okay, so once I do this, then I achieve this 30 for this stream. Or, you know, I just completely satisfy the cold stream, and this is the objective below the pinch. So below the pinch, you need to satisfy all your cold streams. Above the pinch, you need to satisfy all your hot streams. Most of the time, it's just straightforward. However, sometimes you need to do this manipulation. Take note of it, be aware of it when doing your calculations. Okay, so this is what we did. This is what the slide implies. So if you're reading it, just don't get confused. There is no violation. 30, okay, nice. So this is done. I satisfied all my cold streams. And then I can add some cooling below the pinch. And I determine the cooling requirement remaining for my hot stream by basically 90 minus 30, this is 60. Right, multiplied by 1.5 is 90. I satisfied 30 of these by using this transfer, so I can add cooling worth of 60 units of energy, okay? And basically all the cooling utilities. So then you add the cooling utilities as needed, and this number, your cooling utilities number, should be equivalent to your the number you calculated from your cascade diagram, okay? So the cooling utility number should equal to the number at the bottom of your cascade right here. You know, if you do your cascade, you add your QH min. At the top, you have a pinch point here or anywhere equal to 0. And then whatever is left at the bottom is your QC. Okay? So this is the idea below the pinch. Again, the 2 rules which apply below the pinch, CP hot greater than CP cold, and you cannot have thing below the pinch. Please remember these when moving forward. Okay, so after doing all your connections, sorry, you have your completed design right here. So I have all my streams connected, everything satisfied, and this design meets the minimum, or, you know, the maximum energy requirement targets. QH minimum is 20 kilowatts and QC minimum is equal to 60 kilowatts, okay? So this is very important for you to try and follow this procedure, try and understand it, see what's going on, all this stuff. Okay, so let's try to do, or let's recap the steps. Step number 1, you define the pinch temperature, you define the QH minimum, you define the QC minimum, and these are called your MER targets. And again, we do this using either graphical approach, so 2 ways to do it, graphical, and if you're doing graphical, you need to determine your hot composite, you need to determine your cold composite, you need to shift them close to each other until you get delta T min, and then this becomes your QH, and this becomes your QC. Alternatively, you can do the cascade diagram where we said, you know, you start from your table, I subtract delta T minimum, I arrange the intervals, right? I arrange my intervals, all this stuff, I draw my lines, I calculate summation of CP hot minus summation of CP cold, all this stuff, and this is all in the previous slides and homework 3. So I draw my cascade diagram, all of this stuff, and in this cascade diagram, I find my pinch point, which is the most negative. I add enough heat at the top such that this is equal to 0. The heat I added is QH, and the heat left, or the heat cascading to the bottom is QC, okay? So once you do this, so after this step, I have my pinch temperature, I have QH min, I have QC min. I divide my problem at the pinch. I design the hot end starting above the pinch, right? So, or, you know, left-hand side, whichever you want to call it. And you pair up exchangers according to CP constraints. Immediately above the pinch, this rule applies. CP hot has to be less than CP cold. So this is rule number 1 for above the pinch, and rule number 2 do not use cooled utilities, okay? No cooling above the pinch. On the other hand, below the pinch or your right-hand side, this is your first rule. CP hot has to be greater than CP cold for matching. Let's call this 1. And number 2, there is no heating below pinch. Okay, very important ideas. You need to remember them when doing this diagram. Okay, let's have a look at a couple of examples. Okay. So remember the simple example we were talking about where we had these streams and we said this is a design, how did we get to this design, all this stuff. So let's try to approach it in a logical way. So again, these are your streams. We have these streams and we were given, last time we calculated the pinch point. We said, if you recall last time, we used this example with the cascade diagram or last week, and we found the pinch point to be 70 for the hot, 60 for the cold. We found the QH minimum to be 48, and we found the QC minimum to be 6. Okay, so we have all our numbers. Now let's try and basically design this heat exchange network. So first step, as always, we said we're going to graphically just draw these lines. So I start with my hot stream. I just draw H1 square, whatever, draw a horizontal line, my starting temperature, my final temperature, and I note my CP next to it. The next one, just H2, first temperature, initial, final, CP. Cooled from the right, initial, final, C2, initial, final. Just draw horizontal lines. Give yourself some space, so don't cram them up on the page and then have small diagram. Just give yourself enough space to actually draw them, make errors, you can erase whatever it is. Give yourself some space you can practice. Okay, I did all of this. And then step number 1, I'm going to draw a line down the middle with my pinch points. So I draw a line, the hot pinch is 70 for this case, and the cold pinch is basically 60 for this case. After drawing the pinch, I need to adjust my stream. So in case if one stream exists entirely above the pinch or one cold stream exists entirely on one side of the pinch, I need to adjust for it. So if I look here, this stream goes from 180 to 80, but my pinch point is a 70, right? So this stream actually stops somewhere here. So I need to be careful. And this is a very common error to do where, you forget which direction you're going and you just keep these temperatures. But for the hot stream, it ends at 80. So this side, I need to redraw it such that it stops here. For the second one, 130 to 70, 70 to 40, that's fine. For this one, it goes from 60 to 60. It doesn't make sense. So my cold stream actually starts here. So this C1 does not exist below the pinch, and this H1 does not exist below the pinch. So correct your diagram so that you clearly define your two problems. Okay, this is what we did. Got rid of them, whatever. And now let's have a look at the two problems, right? Let's have a look at the two sides. And again, let's remember the rules. Let's go back a second here. Remember the rules. We said above the pinch, CP hot less than CP cooled, no cooled utilities. Below the pinch, CP hot greater than CP cooled, no hot utilities. Let's so we said above CP hot less than CP cooled. So on this side, I have two rules I need to follow. CP hot has to be less than CP cooled. And number 2, we said what? No cooling, right? No cooling. And on this side, below the pinch, I have basically the reverse rules. CP hot has to be greater than CP cold. And number 2, no heating. And this will be the basis for me to connect these streams. Okay, we can start on any side, it doesn't matter. Just let's start on this side, okay? So I want CP hot because I only have two streams, maybe it might be easy. CP hot greater than CP cold and no heating. So let me look at my cold stream. My first cold stream is C2 because C1 does not exist below the pinch. I look at the CP here. I compare it to the hot stream. So there's no H1 does not exist below the pinch. I do the comparison. Is CP hot greater than or equal to CP cold? 2 greater than 1.8? Yes. So this transfer is valid. So now I just draw my heat exchanger between these two streams, and I need to determine how much heat is being transferred. So let's have a look here. 60 minus 30 multiplied by 1.8. That's how much? 30 plus, what's 3 by 8? 54, I think. 54. And now let's look at this stream. 70 minus 40, that's what, 30 multiplied by 2. So this stream actually has 60 units, and this stream has 54 units. I can transfer 54 using this exchanger, and I have 6 units left for which I need for this hot stream. And again, I need to check it's a hot stream, so it will be a cooling utility. So I'm not violating the rule, and this utility will be 6. So I'm not violating either of these rules. So this stream is done. This stream is done. I'm able to take these 54 units of energy or provide these 54 units of energy. And I'm also being able to cool this stream completely. Good, done. All right, so this side is done. Our number matches the QC minimum. We're good. Let's look at the left-hand side. So again, CP hot has to be less than or equal to CP cooled. Let me write the CP values on this side, just so that it's easier to visualize instead of looking over there every time. Anyways, so let's have a look here. CP hot less than or equal to CP cold. I'm going to compare H1 to C1. Let me compare these two guys. Is CP hot less than or equal to CP cold? 1 less than 4? Yeah, it's less than 4. Okay, it makes sense. Let me connect the heat exchanger between these two guys. So I'm gonna draw here a circle, connect it to here, second circle. 180 minus 80. So how much enthalpy is available in the stream above the pinch? 180 minus 80, that's what, 100 multiplied by 1. So I have 100 here. That's calculated for all of them actually. 130 minus 70, 60 multiplied by 2. I have 120 here. 100 minus 60, 40 multiplied by 4. 160. 120 minus 60. That's what? 120 minus 60 is 60 multiplied by 1.8. That's what? 6 times 8 is what? I don't remember actually. I think it's 108, maybe. Let's calculate this. 60 multiplied by 1.8, it's 108. Good, so we have these numbers right here. Okay. Okay, so I'm connecting these two guys. This stream has 100. This stream needs 100. So this will have 100, right? So this connection will have 100. And this stream satisfied, good to go. Let me look at H2. Let's double check. Is 2 less than 4? Yes, 2 is less than 4. So I can make this connection as well. So let me draw this connection between 2 and 4. This stream requires 108. Sorry, this is the wrong connection. So I'm connecting 2 to 4. So this stream, I already satisfied 100, so I have 60 left in this stream. So I have 60 units of energy left. Just take a note of this. Then I'm connecting 2 to 4, CP hot less than CP cold, 2 less than 4. Yes, so I'm just going to connect these two guys right here. And let's have a look. How much energy am I transferring? Sorry, 120, and this needs 60, so I'm transferring 60. So there is 60 units of energy right here, and this stream is satisfied. Okay, so now if I look at this design above the pinch, okay, there is no cooling above the pinch, so I can't really cool the stream. So you have one of two choices. You can either, do a split stream, or alternatively, we can reconfigure our design. So, first of all, I tried 1 and 4, but 1 and 4 works, but I tried H1 and C1, basically 1 and 4, but H1 and C2 also works, 1 and 1.8. So if you want to avoid splitting the streams, if you split the streams and do the calculations, you're gonna get the right number. It's just simple math. But if you want to avoid splitting the streams and you reach a situation, it's always worthwhile to take a look at the second option. And this is what we're gonna do now. Okay, this is what we're gonna do now. So the second option would be, erase this guy. Let me erase this guy. Second option would be, instead of connecting 1 and 4, I'm gonna try and connect 1. Okay. I'm gonna connect 1 and 1.8. I'll try to connect 1 with 1.8. Is CP hot less than CP cold? Yes, 1 is less than 1.8. So let's try and connect these two guys right here. This stream has 160. This stream needs 108, so this will be 108, and then I get rid of C2. It's satisfied, and in this case, H1 will still have some energy left. So H1, no, it's actually 100, right? It's not. Is it 100? Yeah, it's 100. So I actually just only provided 100 in this case. So this is fine. So I'm able to transfer 100. So now H1 is satisfied, but C1, I still have 8 units of energy left, right? So I still have 8 left on the stream. Okay, good. So now let me have a look, see if I could transfer heat between the second stream. So H1 is done. Let me move to H2 and compare it to C1. 2 less than 4, CP hot less than CP cold. Yes, I'm going to connect these two guys here as well. And the energy transferred will be what? So this stream has 120. This stream requires 160. So I'm going to transfer all of the 120 from the hot stream. So this stream is satisfied. So this stream requires 40. So now I have 40 and 80. My 2 hot streams are required, so I'm not going to do any cooling above the pinch. So this is satisfied. So here I'm going to add 2 coolers. This one with a 40 and this one with an 8, and this satisfies this requirement. Okay. Alternatively, I can connect this stream to both of them. So I can connect, instead of having 2 coolers here, I can connect H2 to C2 and then connect H2 to C1 and then just have one cooling utility. There are a bunch of different ways to do it. However, just find the way which satisfies this mathematically. And again, the rules you follow are this. It's most of the time it's straightforward. However, sometimes you need to think about it, try and find the best approach. Okay, well, let me erase everything on this slide so that you can see what's going on. So we connected 2 to 4. So CP again here, CP hot has to be less than or equal to CP cooled, and here CP hot has to be greater than or equal to CP cooled. There is no cooling here. there is no heating here. I connect these two, determine the energy, 120. This works. I connect these two, transfer the 100. Okay, and then I have a cooling heater here with 40, and a second heater with 8, and this satisfies the energy requirements. Okay, and basically this satisfies your QH. So the summary of heat integration here is, if I give you data on hot and cold streams, you should be able to compute the pinch temperatures, compute the maximum energy recovery targets, which is your QH minimum and your QC minimum, and then design your heat exchange network. And when a few general comments when problem solving, always outline the solution steps in generic terms before plugging in numbers. So always make sure you know what the procedure you're going to follow. Whenever you make a decision, make sure you argue why you made it. This is also very important. If you get stuck on a problem because you're missing one piece of information, make an assumption, state it, then show you know how to solve a problem, right? If you get stuck somewhere and you have no idea how to proceed, just write your logic, okay? You're gonna get partial credit, or it will help you think through the problem as well. But don't panic, just there's a solution out there. Okay. So we have let's try and do this problem. Let's try doing it using the algebraic method, okay? And the next bunch of few slides are going to show you a solution, but I want to solve this problem on the whiteboard just so they can see how I'm going to proceed through it. Okay, so let me write these metrics down. So I have 4 streams, 1, 2, 3, 4, 170 to 30, 140 to 30, 60 to 180, and 30 to 105. My CP are 2, 4, 3, 2.6 kilowatt per degree Celsius, and these are all degree Celsius. And my delta T minimum is equal to 10 degrees Celsius. Okay, let's have a look and try to do it on the blackboard and then double check with the slides. Hopefully we get the same answer, right? Or the whiteboard in this case. Okay, let me maximize the screen right here. Okay, let me write the given. So you're given 4 streams. Basically 1, 2, 3, 4. My source temperatures in degrees Celsius, right? Oops. My source temperatures are 170, 140, 60, and 30, and these are in degrees Celsius. My target temperatures in degrees Celsius as well are 30, 30, 180, and 105. And my CP, which is in kilowatt per degree Celsius, sorry, is 2, 4, 3, 2.6, and you're given that delta T minimum is equal to 10 degrees Celsius. Okay, so let's try to do it using the algebraic method. So I'm going to follow algebraic method right here. And if you recall, step 1, subtract delta T minimum from the hot temperatures, right? So which of these streams are hot? Which of these streams are cold? So this one is starting at 170 going to 30. This one going 140 to 30. So these two are hot. So let me just rename them. Let me rename them H1, H2. I'm gonna rename this guy C1, and C2, because this is a cool stream, this is a cool stream. So I'm going to subtract delta T minimum from the hot temperatures. So now I'm just going to rewrite it as H1. Delta T minimum is 10, so it's going to become 160, 22. And again, this is T source, T target, CP. H2 is 130, 24. C1 is 60, 183. And C2 is 30, 105, 2.6. So all I did here, I just subtracted delta T minimum, which is 10, from my hot temperatures and from all the temperatures in the hot stream. Good. So now let's move on to step 2. Let me change the color here. Why not? Okay. So step 2 now. I'm gonna arrange my temperatures from hot to cold. Okay. Arrange temperatures from highest to lowest. Okay. And then after this, I'm gonna define intervals and calculate summation of CP hot minus summation of CP cold. Okay, let's do it. So how do I define what's my highest temperature here? It's 180, right? One second, there's okay. Before we continue, let me just tell you something so that matches these slides. These are actually the temperatures after subtracting 10 degrees, okay? So these are the temperatures after subtracting 10 degrees. So initially my temperatures were 180 to 40, 150 to 40, okay? So just be aware of this on the slide. So I'm gonna fix this while talking on the whiteboard. The steps doesn't change, but I want the numbers to match what's listed on your on your slides. Okay, let me do this. Okay, share. So just be aware that, you know, what you're given is actually the problem is actually 180 minus 40 and 150 minus 30. And then when I subtract the delta T minimum, I get the numbers shown on your slide, okay? So the first step was done for you on the slide to make it easier, but you know, just be aware of it. So after subtracting delta T minimum, I get 170, 30, and 140, 30 as well. And this one has to be 150, 40, right? Speaker. And this is what's given on the slide, right? This is what's given on the slide. So just be aware of this. I'm on the slide you're already given. Your step 1 was already done for you. Doesn't matter. So you're given a bunch of data, 180 to 40, hot streams, cold streams, whatever. First step, you subtract delta T minimum, and you get your numbers. This is the easy part. We didn't really do anything so far. Okay. After subtracting delta T minimum, I'm gonna arrange my temperatures from the highest to the lowest. I'm gonna define my intervals, and I'm gonna calculate CP hot minus CP cold. So let me start arranging my temperatures from hottest to coldest. My hottest temperature in this case is 180. So I'm gonna basically, this is how I do it. Find a way which works for you. and go for it. Doesn't matter. So my highest temperature is 180. My second highest temperature in this case is 70. So I'm just going to draw a line here, 170, 170. So this is my highest, this is my second highest. My third highest will be 140, right? 140. Okay, my next highest is 105, right? And again, these problems take time, okay? So just get used to, taking a bunch of time to do it. My next one is 60. So next one is 60. And my final one here is 30. Good. So now after arranging them from highest to lowest, you can clearly see that I have, how many intervals here? I have 1, 2, 3, 4, and 5 intervals. Some books, or define this as an interval as well because you have your cooling utility, but it doesn't really matter. It doesn't affect anything. So you don't really need to worry about it at this point. So usually I don't define this last interval. It doesn't affect the math. It's just a cosmetic thing. Okay, so after defining my intervals, so again, let me just label them. So these are my intervals. These are my temperatures. I'm going to start plotting my streams. So let me change the color here. Let me pick purple. Let's see. So I'm going to plot my streams. So H1 goes from, let's see. H1 goes from 170 to 30. So I'm going to write H1 right here. It starts at 170. And it goes all the way to 30. So I'm just going to draw a straight line down to 30. And the CP for H1 is 2. H2 goes from 140 to 30. So this is H2, right? C1 goes from 60 to 180. So C2 is from 60 all the way to 180. Sorry, C1. And C2 goes from 30 to 105. And C2 goes from 30 to 105. Okay, so these are my streams, and I have my intervals. So now I'm going to calculate this parameter right here, which is summation of CP hot minus summation of CP cold, right? So here I'm going to calculate basically, doesn't matter. Where's this guy? CP hot minus summation of CP cold for each stream, for each interval, sorry. So let me look at interval number 1. Summation of CP hot is 0, there are no hot streams. CP cold, I have 1, which is C1, minus 3, so this is minus 3. And let me also calculate delta H, which is equal to delta T, or delta T multiplied by CP hot minus summation CP cold. And in this case, delta T is 10 multiplied by minus 3, and this is equal to minus 30 kilowatts. Okay, let me look at the second interval. Summation of CP hot is equal to H1. So CP for H1 is 2. Summation of CP cold is C1, 3. This is equal to minus 1. And then the delta H in this case is what? Delta T is 170 minus 40, so it's 30 minus 1 is equal to minus 30. And okay, so go to the third interval here. Summation of CP hot is H1 plus H2, so it's equal to 2 plus 4, minus summation of CP cold, I only have C1, minus 3, so this is what, 6 minus 3 is 3, and the delta H for this interval is 140 minus 105. This is 35 multiplied by 3 is equal to what? 90, 15, 105, right? 105 kilowatts, kilowatts. Good. And then my fourth interval, summation of CP hot, I have H1 and H2. So in this case, I have 2 plus 4 minus summation of CP cooled. I have both of them as well, 3 plus 2.6. So this is what, 6 minus 5.6. So this is 0.4. Okay, and delta H in this case is 105 minus 60. This is 45 multiplied by 0.4. So this is what, 16. 16.2 or something like that. Let me just verify this. So we said what, 45 multiplied by 0.4, that's 18 actually. Good. So yeah, because 5 by 0.4 is 2. So this is 18 kilowatts. And then my final interval right here, summation of CP hot is 2 plus 4 minus summation of CP cooled, which is 2.6. And in this case, 6 minus 2.6, 3.4, and 3.4 multiplied by 30, and this is 3.4 multiplied by 30. This is 102 kilowatts. 102 kilowatts. Good. So I have my intervals. I have all this nice information. I calculated my summation of CP hot minus CP cooled. I calculated my heat for each interval. So I have all the data I need to really draw my cascade diagram, right? So after doing this, third step is to draw the cascade diagram. So let me save this whiteboard. I'm going to save it. And now I'm going to erase this side right here so that we can draw our cascade diagram. Okay, good. Step 3 now becomes draw your cascade diagram. Okay, so how do you draw the cascade diagram? If you recall, I'm going to start with my first temperature. So T1, this temperature right here is equal to, oh, what's this? Okay. T1 is equal to 180, and then I'm going to draw a line here. I'm going to draw a box. Is delta H1 minus 30, and I'm just translating this information into a figure. Minus 30, and here I have T2 is equal to 170. I have a second box. Delta H is minus 30 again. Delta H2 is equal to minus 30. I have a third box right here, T3, so 170 to 140. My third delta H is equal to 105, right? And then I have another box here, and this is T4, 105, and delta H4 is equal to 18. And then I have one box here. So this is T5 is equal to 60. And delta H after 18 is what, 102? Delta H5 is equal to 102, right? And I have my final temperature, which is the last one, T6, is equal to 50. Good, so I just translated this information into this figure. And we need to note one thing here. So now I'm going to calculate the QH. So let me change the color. So I'm going to calculate the QH assuming that the starting point is 0. So QH here is equal to 0. Q1 is 0 minus 30. Right? So this is Q1. Q2 minus 30 minus 30 minus 60. Q3 minus 60 plus 105 is 45. Q4, 45 minus 18 is 63, right? And Q5 at the bottom here, 63 plus 102 is 165. So I just drew my cascade diagram. That's it. Okay, so now after drawing my cascade diagram, what's the next step? Step 4. Find the most negative point, most negative Q. And this is very important. So in this case, the most negative Q is at this point, right? Q, this is the most negative, and this is my pinch temperature, okay? So after finding the most negative Q, the next step would be add enough heat to make it 0, right? To make the most negative point 0. So what I'm gonna do, I'm gonna add 60 kilowatts to the top. You can redraw the diagram or you can just add 60, right? So if I add 60 kilowatts to the top, Q1 becomes 30, 60 minus 30 is 30. Q2 becomes 30 minus 30 is 0. Q3 becomes 0 plus 105 is 105. Q4 becomes 105 plus 18 is 123. And Q4 becomes 123, and Q5, 123 plus 102 becomes 225. And now, after doing this, I have the 3 pieces of information I want. And these 3 pieces of information are this number right here. This is your QH minimum. This number right here, this is your QC minimum. And this guy right here, which is your pinch temperature. Okay, so this is very important. So now I have my QH minimum, I have my QC minimum, and I have my pinch temperature. One thing to remember is that this is your cooled pinch, right? This is your cooled pinch. This is DC pinch. So let's summarize what we have at this stage. So at this stage, I have this information right here. I have TC pinch is equal to 140. So basically, this means that TH pinch is equal to 150, right? I have my QH minimum is equal to 60 kilowatt, and of course these are degrees Celsius, these are degrees Celsius. And I also have my QC minimum equals 225 kilowatts, right? So I have this information right here. And I'm going to use this information to design my heat exchange network, right? So I'm going to use it, design the heat exchange network. Okay, let me save this guy. And now let me erase, or let me clear all the drawings. Okay, let's, so after doing this, you open a new page or start a new sheet, whatever it is, and let's rewrite our given. Let's rewrite the initial streams in addition to the information we just got. So the initial streams we had, if you recall, I had H1 going from 180 to 40. So this is T source, T target, CP with a CP of 2. We had H2 going from 150 to 40, right? 150 to 40 with a CP of 4. I have C1 going from 60 to 180, right? 60. Is it 180 or 170? 1 second. 60 to 180, sorry. So I have C1 going from 60 to 180. 180 and a CP of 3. And I have C2 going from 30 to 105 with a CP of 2.6. Okay, good. And from the cascade diagram, I have 3 pieces of information. TC pinch is 140 degrees Celsius, and TH pinch is equal to 150 degrees Celsius because the delta T is 10. I know my QH minimum was 60, and my QC minimum 225. Okay, so let's start designing this network right here. So I said the first step is I'm going to just start drawing. So let's say H1, and I'll draw a horizontal line like this. I'll just write 180, 40. And you can write CP, so you can write CP here, and I'm gonna say CP is 2. It's just given. Let me give myself more space for H2. And then I'm going to draw H2 here. H2 goes from 150 all the way to 40, and CP is 4. And then I'm going to draw here C1, and it goes from 60 to 180 with a CP of 3. And finally, C2, it goes from 30 to 105, 30 to 105 with a CP of 2.6. Sounds good. So this is step 1, just draw them. Said step 2, I'm gonna draw a line down the middle at my pinch point. Okay. Let me do this. I'm gonna draw this line using black here ink. So I'm going to divide this problem here at the pinch point. And we said the hot pinch is 150. So for the hot streams, this is 150. And the cold pinch is 140. So this guy right here is 140. Okay, once I do this, now I'm gonna readjust my streams to match this pinch point. So let me have a look here. 180 to 150, 150 to 40, that's fine. 150 to 40, 150 to 150, 150 to 40. So actually H2 does not exist above the pinch, right? So H2 actually starts here. This is where H2 starts, okay? So there is no H2 above the pinch. I don't need to worry about it. 60 to 140, 140 to 180, that's fine. 30 to 140, 140 to 105, that doesn't make sense, right? So actually C2 does not exist above the pinch either, right? So C2 does not exist here. and C2 just stops here at 105. It stops above the pinch at 105. Okay, just be careful. Don't use 140. Just use the temperatures you have for the streams. Okay, after I'm done with this, now I'm gonna I have two problems, right? I have this problem, this side right here, above the pinch and below the pinch, and we're just going to follow the rules. So before doing this, let me rewrite the CP values. So CP here, just to avoid looking at the other side, 2, 4, 3, 2.6. So let's start above the pinch. Let's start on the left-hand side. So above the pinch, we have two rules, we said. What were the rules? Guys, let's go back to the slides and remember them. Slide. It's always good. Just go double check you're doing the right thing. It's very easy to mix up these rules. And if you mix them up, you'll always get numbers, right? It's just math, but the numbers are junk. Okay. Anyways, going back. So above the pinch, we're following this rule. We said CP hot has to be less than or equal to CP cooled, is rule number 1. And rule number 2, above the pinch, is no cooling. Whereas below the pinch, my first rule is that CP hot has to be greater or equal to CP cooled. And rule number 2, no heating. Okay, let's have a look here. Which are the best combinations? So before starting anything, what I like to do is I like to calculate the delta H's. Gives me sort of a general idea of what I want to do. So for H1, I need to go above the pinch 180 to 150. That's 30 multiplied by 2. So delta H for this guy is 60, right? So you can add actually a delta H here if you want. 180 minus 50, 30 by 2 is 60. 150, so this guy doesn't exist above the pinch. 180 minus 140, this is 120. Sorry, 180 minus 140, this is 40 multiplied by 3. This is 120, and this guy doesn't exist above the pinch. And then I'm going to do this on this side as well. So below the pinch, 150 minus 40, this is 110 multiplied by 2, 220. 150 minus 40, again 110 multiplied by 4, this is 440. 140 to 60, this is 80 multiplied by 3, this is, yeah, this is 240, right? And 105 from 103, 105 minus 30, this is what, 75? 105 minus 30, 75 multiplied by 2.6, this is 195. Okay, so I have my enthalpies above and below the pinch. I know what I want to achieve. So now let's try matching these streams. So above the pinch, I only have H1 and C1. Let's see if this match works. Is CP hot less than CP cooled? Is 2 less than 4? Yes. So I can connect these guys. So I'm going to draw one heat exchanger here, all the way down here. And let's have a look. So this hot stream has 60. This cold stream has 120. So I'm going to transfer all the 60 from this stream to this stream. So H1 is satisfied. And then C1 still needs 60, right? Because it has an overall delta H of 120. I met 60 and I have 60 left. So I add a heater. So because it's a cold stream, I add a heater. And this heater is going to add 60. And this is my QH min. This matches this number. We're good. So above the pinch is done. Let's have a look on the other side below the pinch. Let's start our analysis. So CP hot has to be greater than CP cooled. Okay, let me start with the first one. 2 greater than 3. Is this possible? No, it's not possible. 2 greater than 2.6. Is this possible? No, it's not possible. So I really can't connect 2 to anyone. Let's have a look at 4. 4 to 3, is it possible? CP hot greater than CP cold, yes. And so let's connect them. Okay, let's have, so I'm going to connect the heat exchanger from this stream to this stream. This stream has 440 kilowatts to give. This stream needs 240. So I'm just going to transfer 240 kilowatts and satisfy this stream. So now this stream has 200 left, right? I satisfied 240, I still have 200 left. Let's see, can I transfer it to this guy? So 4 to 2.6, does this transfer work? Yeah, because, you know, CP hot is greater than CP cold. So let me connect the second heat exchanger here, sorry. Second heat exchanger here, and all the way here. And this one needs 195, this one has 200 left, so I'm gonna transfer 195 kilowatts. So C2 is satisfied. So below the pinch, I satisfied all my cooling streams. So I'm not violating the rules. I'm not gonna heat below the pinch, that's good. So now I have to cool these guys to meet the requirements. So this one, I can match it with anyone. So I'll just add one big cooler with a 220 to just meet the entire demand of this stream. So this is done. And this stream, I still have some energy I need to deal with, right? Because it gave 240 to this guy and it gave 195 to this guy. So it still has 5 left. So I'm going to add a small heater, a small cooler here, heat exchanger, sorry, with 5 kilowatts, right? So 220 plus 5 is 225. So my QC minimum is equal to 225. And this matches this number. So my calculation is correct. Okay, so we just followed the approach. Again, first step, I draw my lines, I define my pinch point, I start matching the streams using the laws above the pinch and below the pinch until I get the design which matches the numbers I have. Let me save this guy as well. And this is really how you solve this problem. So let's go to the slides. And the slides basically show this. This is not it. This is the example, and this just shows this. The same way we solved it on the whiteboard. You can go through it, whichever one works for you. But basically what we did, I drew my streams on my pinch point, readjusted my streams for the pinch, you know, to avoid having errors, to make it easier for me to solve. Match the streams, all this stuff, you know, check the QH, check the QC, etc., until we got our final number. Okay. And this was example 1. Let's solve a second example. Let's solve a second example just so that we see what's going on. Okay, so example 2. Let's go back to the whiteboard and do a second example just so that you see what's going on. Yeah, this lecture is a bit long, but you know, it's one of the more important ones. And next week we won't have a lecture, we'll sort of have a review. So you have 2 weeks to really go over this lecture. Okay, let me share the whiteboard again. And we already saved this, right? We saved this. So I'm going to clear all my drawings. And I'm going to start example 2. Okay, let's have a look here. What's this mouse? Example 2. You're given a bunch of information again. So you're given stream 1, stream 2, stream 3, stream 4. Your source temperatures and your target temperatures. So your source temperatures are 170, target temperature 50. Source temperature is 180. Your target temperature is 60. And your CP is 3. And of course, this is in degrees Celsius. This is in degrees Celsius. This is in kilowatt per degree Celsius. Your second stream is 150 to 30, and the CP is 1. Your third stream is 30 to 135. Your CP is 2, and your final stream is 80 to 140, and your CP is 5. So now we're just going to do the same thing. It's a tedious process, but this is how you do it, okay? This is how you do this design approach. Step 1, subtract delta T minimum from the hot streams. So I'm going to rearrange my hot streams so I have which ones are the hot. This is H1, right? This is H2, this is C1, this is C2. So I'm going to rewrite this. So I have H1 here. I'm going to have, what's delta T minimum? You're given delta T minimum to be equal to 10. So H1, it's going to be 170, 53. And again, this is T source, T target, CP. Units are the same. H2 will be 140 to 20 with 1. H3 will be 30, 135 with 2. CP is 2, sorry, this is not H3, this is C1. Yeah, just be careful. Yeah, it's a tedious process. So you tend to sort of go into some sort of strange autopilot mode where you're doing a lot of mistakes, right? So I have C2 now is 80, 140, and 5. Okay, so these are my streams after step number 1. Step number 2 is where I'm going to arrange my temperatures. So step number 2. Arrange temperatures from highest to lowest. Find my intervals. And calculate summation of CP hot minus CP cold. So let's start by arranging the temperatures. So what's my hottest temperature here? It's 170, right? So my hottest temperature in this case is 170. So this is how I draw it, right? So I say T1 is 170, and you just, where's that? Okay. T2 is 140, so 170, then 140, so T2 140. T, so 140, this guy and this guy are done. T3 is 135. Okay, T4 is 80. T5 is 50. T6 is 30. And T7 is 20. Okay, so how many intervals do I have? I have 1, 2, 3, 4, 5, and 6 intervals. Okay, sounds good. So now let's plot our streams. I like to plot the streams. It makes it easier for me to calculate summation CP hot minus CP cold. Okay, so H1 goes from 170 to 50. So I start here. H1 goes from 170 all the way down to 50. H2 goes from 140 to 20. So I have here H2 goes from 140 all the way down to 20. C1 goes from 30 to 135. So C1 goes from 30 all the way up to 135. And C2 goes from 80 to 140. So C2 goes from 80 all the way to 140. So these are my streams. So now let's calculate the required parameters. So I'm going to calculate summation of CP hot minus summation of CP cold for each interval. And I'm also going to calculate delta H, which is equal to, summation of CP hot minus summation of CP cold multiplied by delta T. So let's have a look here. In interval number 1, summation of CP hot is what? I only have H1 here, and this one is 3, so this is equal to 3. In interval number 2, I have two hot streams, H1 and H2. So CP for H1 is 3, CP for H2 is 1, minus summation of CP cold. I only have one cold stream, minus 2. So this is 4 minus 2. This is 2. Right? No. C2 is 5. Yeah, sorry. So 3 plus 1 minus 5. Yeah, just be careful as well, because the math is very simple. You tend to make very simple errors. So 3 plus 1 minus 5. This is minus 1 actually, right? So this is minus 1. Okay, let's look at this interval right here. CP hot, I have the two hot streams, 3 plus 1, and I have the two cold streams as well, minus 2 plus 5, so this is 4 minus 7 minus 3, right? Let's look at this interval. I have both hot streams as well, 3 plus 1 minus C1 only, and C1 is 2. So now here we have the 2. Let's look at this interval. I have one hot stream, which is 1, minus one cold stream, which is 2. So this is minus 1. And finally here, I only have one hot stream with a CP of 1. Okay, so these are the values I have. Now let's calculate the delta H. So in this stream, it's going to be 3 multiplied by delta T, which is 770 minus 140, 30, so it's 90. In this stream, it's going to be minus 1 multiplied by 140 minus 135, it's 5, so this is minus 5. This is the third stream right here, so it's going to be minus 3 multiplied by 135 minus 80, this is 55, right? And this is equal to minus 165, right? Minus 150 minus 15. This guy right here, I have 2 multiplied by 80 minus 50, 30. So this is 60. This guy right here, I have 20 multiplied by minus 1. This is minus 20. Let's keep it consistent. So here I have minus 1 multiplied by 20. This is minus 20. And finally, right here, I have 1 multiplied by 10, and this is 10. Okay, so at this point, I have all my summation of CP hot minus CP cold. I have my delta H's, I have my intervals. So what do I do next? I need to draw my cascade diagram. Okay, so step 3 would be to draw your cascade diagram. So let me erase this guy and let's try to squeeze this cascade diagram right here. So, okay, so let's try and draw the cascade diagram. Let me use a different color. So what's a nice color to use? Use black, doesn't matter. Okay. I'm going to draw my cascade diagram here. So I start off at the top. I have T1 is equal to 170. I draw the first box right here. Delta H1 is 90. I have T2 is equal to 140. I draw my second box. You can possibly, accelerate to this video. I don't know if Blackboard has the ability to accelerate videos, but YouTube does, so you could T3 here is 135. Delta H3 is minus 165. And then I have T4 is equal to 80. Delta H4 is equal to 60. I have T5 is equal to 50. Delta H5 is equal to minus 20. I have T6 is equal to 30, and delta H6 is equal to 10, right? So I have all of them. 1, 2, 3, 4, 5, 6, 90 minus 5 minus 165, 60 minus 20, 10. And I have my final temperature here, T7 is equal to 20, right? So this step number 3, draw your cascade diagram, right? So this is good. And then step number 4 becomes to find the most negative point. So sorry, step number 3, we're not done with step number 3, right? Cascade diagram, and also calculate the delta H's. Very important, just calculate delta H or the Q's. So we start off by Q hot equals 0 plus 90, so Q1 is equal to 90. Q2 is equal to 85. Q3 is equal to 85 minus 165 is what? Minus 80, right? Just double check this. 85 minus 165 is 80, good. So this is minus 80. Q4 is equal to minus 20. Minus 80 plus 60 minus 20. Q5 minus 20 is minus 40. And finally, Q6 here at the bottom, minus 40 plus 10 is minus 30. So at this point, I have my cascade diagram. I have my heating and cooling requirements, all this stuff. So now I need to adjust my cascade diagram. So after doing my cascade diagram here, I need to, step number 4 now becomes to find the most negative and make it 0. So in this case, the most negative point is minus 80, and my pinch point, my cold pinch is 80. So I'm going to add 80 kilowatts at the top. So now my QH is equal to 80, and I'm gonna let this 80 cascade down. So 80 plus 190, Q1 becomes 170. 170 minus 5, Q2 becomes 165. 165 minus 165, Q3 becomes 0. 0 plus 60, Q4 becomes 60, right? 60 minus 20, Q5 becomes 40. 40 plus 10, very bottom, Q6 or QC is equal to 50, right? So now, after doing this step, I have my 3 metrics, which are important to me. These are my QH minimum, right? My QC minimum, and my pinch point. So after this stage, you should have the 3 pieces of information which you need to build your diagram, right? So after step 4, I know that my T pinch is equal to 80, and this is basically cold, and the hot will be 90, right? I also know that my QH minimum is 80 kilowatts, and this is degrees Celsius, of course, degrees Celsius, and I know that my, where is this? Where's this pen? There we go. And I know that my QC minimum is equal to 50 kilowatts. So I have my pinch point, I have my targets, and this is all I need to start building my heat exchange network. So let's start doing this. So let me clear all my drawings and let's try to remember our given first of all before we start our building our network. So I had H1, if you recall, going from 180 to 60 with a CP of 3. Again, T source, T target, CP. I have H2 going from 150 to 30, CP of 1. I have C1 going from 30 to 135 with a CP of 2. And I have C2 going from 80 to 140 with a CP of 5, right? So this is what I have. And then from my cascade diagram, I have these pieces of information. I have TC pinch is 80 degrees Celsius. T hot pinch is equal to 90 degrees Celsius. QH minimum 80 kilowatts. QC minimum 50 kilowatts. Good. Now let's start drawing our diagram. Let's start dealing with this problem. So step 1, graphically, I'm just going to draw the streams, you know. So I have H1 going from 180 to 60, and I'm gonna CP here is 3. Next one, H2 going from 150 to 30. Okay, this is a shocking line. I'll try to make it reasonably. So this is 150 to 30, and CP is 1. I have C1 right here, 30 to 135. There you go. 135, CP of 2. And finally, C2, this guy right here, goes from 80 to 140. 80 to 140 with a CP of 5. Okay, so now I have my streams. Let's draw our pinch point and let's try to adjust for it. So I'm just looking at the solution to make sure we're not dropping a number here anywhere. Okay, good. So now I drew my 4 streams. Very nice. I have my CPs. Let's first of all, let's divide it at the pinch. So we said the pinch point is 80 for the cold and 90 for the hot. So I'm just going to draw a line right here. There you go. And the pinch point for the hot streams will be 90, 90. And for the cool streams will be 80, 80, 80, 80. And now I'm gonna just adjust to make sure that the graphical representation is accurate. So 180 to 90, 90 to 60, that's fine. 150 to 90, 90 to 30, fine. 30 to 80, 80 to 135, fine. 80 to 80, no, you know. So C2 does not exist below the pinch. C2 starts from here. So I'm just going to just scratch it out so that I don't confuse myself. Okay, so now I have my problem. It's divided into 2 parts, above the pinch and below the pinch. Okay, so let's try to remember what do we do above and below the pinch. So again, I have CPs. Let me write my CPs here on this side as well, just to avoid looking. I have 3, I have 1, I have 2, I have 5. And I also like to calculate the delta H's above and below the pinch. So on this side, 90 minus 60 is 30 multiplied by 3 is 90. 90 minus 30 is 60 multiplied by 1, 60. 80 minus 30 is 50 multiplied by 2 is 100. and there's nothing here. And on this side, the delta H is 180 minus 90, 90 multiplied by 3, so what, 270, right? 150 minus 90 is 60 multiplied by 1 is 60. 135 minus 80 is 55 multiplied by 2 is 110. 140 minus 80, 60 multiplied by 5, right? 140 minus 8, 60, this is 300. There's a lot of energy on this side. It's fine. And now let's try to remember the laws of the game. You remember what they were? Let me have a look here. It's always good to just always look at them, you know. It's very easy to make a mistake with these long processes. So we said above the pinch, I have my CP hot has to be less than CP cold, and there's no cooling. So let me go to my whiteboard here. So the rules above the pinch, CP hot has to be less than CP cooled, and number 2, no cooling. And below the pinch, I have CP hot has to be greater than or equal to CP cold, and number 2, no heating. Good. So let's try and make sense of this. Let's try and design our network. Okay. Yeah. Okay, let's try to design our network. Let's start on this side, it doesn't matter. So I need CP hot to be greater than CP cold. So let me start comparing. H1 with C1, does this work? CP hot greater than CP cold? Yeah, it works. So let's do this transfer. Okay. One second. Okay, let's just continue our matching. So CP hot goes to CP cold. I can do this. Does this connection make sense? Yes. CP, so H1 can be connected to C1. H1 can also be connected, can H1 be connected to C5? You know, no. What are we doing? Doesn't make sense at all, right? Let's go back. Let's calibrate our brains again. CP hot H1 with C1. Does this work? Is CP hot less than CP cold? This does not work, right? So let me move on to the second guy. Is CP hot less than CP cold? Yes. So this transfer works. So I'm going to connect H1 to C2. Okay, so I'm going to connect this line all the way to this line, and this stream requires 300. This stream has 270, so I'm just going to transfer all the 270 from my hot stream to my cold stream. So this is satisfied, H1 is done, and I still have 30 here, which I need to give the stream. Okay, so H1 is done. Let me look at H2. H2, I have CP is 1. Can I do H2 to C1? Is CP hot less than CP cold? Yes. I can also do H2 to C2 because 1 is less than 5. But let's connect these two streams first of all. So I'm going to connect these two streams. And I have basically H2 to C1, and H2 has 60 kilowatts, C1 has 110. So I'm just going to transfer all of the 60 to this stream. And basically this still needs 50, right? And this one still needs 30. So H1 and H2 are done. So now I need to, complete the balance by adding heating utilities above the pinch. So because both the hot streams are balanced, are done, I'm not adding any cooling. I don't have any cooling requirement. So this satisfies this rule. This means that my numbers make sense. So I'm going to add a heater here, H1, and this heater is going to add 50 to satisfy this stream. And then I'm going to add H2 here, and this heater is going to add 30 to satisfy this stream, and 50 plus 30, QC is 80, and this matches the QC minimum. So this system above the pinch is correct. My numbers are fine. Let's move below the pinch right here. So I need the CP hot to be greater than the CP cold. Let me compare the first hot stream to the first cold stream. Is CP of H1 greater than CP of C1? Yes. So I can make this transfer. So let's connect these guys. Okay, so this one has 90. This one needs 100. So I'm going to transfer all the 90 from H1 to C1. And then this means that H1 below the pinch is satisfied. Done. Let's have a look here. Let's have a look at this second stream. So this stream C1 still has 10, which has satisfied, and it's the only cold stream below the pinch. Okay, and I can't have any heating, so I cannot really heat using this stream. So let me have a look, and this stream is done, so let's have a look at the second stream. Can I transfer heat this way? I cannot transfer heat this way. Okay, so what do you do in this case? So in this case, there is no way I can add heating. It does not make thermodynamic sense. So in this case, what I'm going to do is I'm going to add a split, right? I'm going to split the stream into two streams, right? Let's see which split makes sense. Let's try to do an algebraic. Let's try to write an algebraic problem here. So this stream has 90. So if I satisfy 90, I only have 10. So I want to split the stream in a way in which basically I still meet all of this 90. So if I look at the enthalpy of stream number 1, it's 90, right? Has to be equal to this enthalpy, or basically 50 multiplied by x. And the x here, which is a split, will be, let's try to calculate it. 50 divided by 90 is going to be 0.55. So if I split the stream into two streams, right? If I split the stream into two streams, one is basically 1.11, and the second one is 0.88. The amount of heat in the stream should satisfy the heating requirement. No, this doesn't make sense. This calculation is wrong. Let's think about it. Let's try to do this calculation properly. So I have this stream has a CP. Let's move up here. So I have a stream which has a CP of 2 and has an energy of 100, right? So stream has a CP of 2 and an energy of 100. I need to split it into two streams, basically M1 and M2, one which has an energy of 90 and the other has an energy of 10, right? So what's the way? Okay, so in order to achieve this, I need to recognize that basically 2 is equal to 50 multiplied by 2 is 100, and instead of using M1, let me use CP1, right? So I'll have CP1, so 50 multiplied by C, or, let's not use CP1 to avoid confusion. Let's call it X, and this is the first split is equal to 90, and then 50 into 2 minus X is equal to 10, right? And this will be the first split, this will be the second strip split, and if I calculate X here, So 1.8 here, for some reason I divided 5 by 9, it should be 9 by 5. In this case, x is equal to 0.2. So if I split the stream into basically two streams, the first one has a CP of 1.8, and the second one having a CP of 0.2, then this transfer becomes possible, right? So this transfer becomes possible, and now I can transfer the rest of the energy from C2 or H2 to C1. So I transferred 90 from this stream, so this first split is satisfied. And let's draw the split this way. It's always better to draw it this way. No, not this color. Okay, so I'm going to do this split this way. And this stream has 0.2, so it has an overall enthalpy of 10. I'm going to connect this guy to this guy. So 0.2 multiplied by 50 is 10. And so this will be 10, and this will be 90. So then the overall C1 becomes satisfied, and this will transfer 10. How much energy do I have left here? 60 minus 10 is 50, so I need to add a cooling requirement with 50, and this is the only cooling requirement here, and this number matches this number, so this makes sense. So in this problem, or this is a typical type of problem, where you have some excess energy left on one of the sides, but you cannot violate the rules above or below the pinch, so you need to use a split stream. And determining the best split stream really requires some algebra. Think through this algebra, it does make sense. If it doesn't make sense or you're not seeing it, it's just a mass balance. Come to office hours, we're going to talk about it in more details, okay? But basically, this is the end of this lecture. It's dragged on a bit, I know. But next week there won't be any lecture. We'll just review for the exam, and then the week after you have your test. And then after that, we're just going to have a very, it's going to get, your motivation should shift towards your project, and we're going to have a couple of very short lectures, okay? So this is the end of week number 8. Thank you very much. Please come to office hours if you have any questions. Don't hesitate to reach out. Next week is going to be a review. Homework solutions will be posted. Take your time, try to learn the steps, and prepare yourself for the test. Thank you very much.